Um, the project starts with the concept that many technologies involve the interaction of carbon with CO2. After I submitted the abstract, I decided to put a subtitle that emphasizes our focus of the study at this moment. The result of study really demonstrate the advantage of this study in gasification, carbon utilization, and carbon capture. This is an outline of our study. The technology driving force will be discussed first. Then we're going to discuss the biochar applications. Our study of biochar has demonstrated the benefit of a pretreatment of biochar before gasification, and also some of the chemistry and the physical phenomena have implied the advantage of carbon utilization and carbon capture. Then I will discuss how these concepts are put together for a very simple study. Then I will discuss our experimental result, and then I will discuss our plan, our technology benefit and the plan in the future. Technology driving force come from the need to develop not only carbon capture process, but also to dispose the captured CO2. So the captured CO2, both process, I should say, the CO2 capture and the carbon utilization, many processes involve CO2 in contact with carbonaceous material. So we decide to study these interactions, particularly in the photochemical interactions. This is a scientist's dream to fix CO2 on carbonaceous material and then bring the carbonaceous material to a higher energy level so we can reburn the carbon. So this is the intention. This is also our dream. And we study ultrasound, the effect of ultrasound for a couple of specific reasons which will be discussed shortly. And the interaction of CO2, supercritical CO2, on carbon treatment process have some unique discovery in the past. So this is a part of our incentive. This slide shows the key result from our study. We first notice the minerals are removed. After the treatment of biochar with CO2 and the water and the ultrasonic and photochemical treatment. We also notice hydrogen attachment, 9% of hydrogen attachment. It has to come from water. And we also notice the significant 13% of carbon attachment on biochar. And there's not much oxygen changes. I could say small change in oxygen reduction, but that's within the experimental error. So all this observation bring the heating value of biochar increase by 50%. This is remarkable. We predict that, but we couldn't believe the effect is so strong. And also, the key result, one of the key results is biochar contains stack of graphene material, graphite oxide material, which can be broken off by ultrasound and also photochemical interactions. So our data seem to improve that. That caused the reactivity of biochar to increase. Some of the chemistry we observed, because graphene oxide is a highly reactive material, and we are thinking to functionalize the graphene oxide so that it can be used to capture CO2. And we also believe ultrasound and the photochemical interactions can break off, can extrafoliate the graphene oxide clusters so that the graphene oxide layers, single layers of graphene oxide, can be used as the building blocks for capturing CO2. This slide discusses the recent emphasis of gasification process. At the bottom, you see this is a traditional gasification process use steam to gasify the carbonaceous material. But nowadays, in the last 2 or 3 years, there is a collaboration between NETL and the EPRI to develop gasification process by using, instead of steam, they are planning to replace steam by CO2 to gasify the carbonaceous material, because CO2 has a much lower heat of vaporization, has a low viscosity, and a lower surface tension. So their estimation is it can save, it will increase the gasification thermal efficiency by 2.8%. And if we add a pretreatment process, treated biochar or co-derived char by CO2 and water, we can, I believe we can further increase the heating value of the gasification process even further. And this is a structure of graphene oxide. It's a single-layered graphene oxide. It's known to have 3 types of functional groups: epoxide group, carboxylic acid group, and a phenolic group. And the first 2 functional groups I mentioned, epoxide and carboxylic acid, can be functionalized by amine. And we believe this type of single-layered material can be clamped on fumed silicate, so that it has a very strong van der Waals force, so it can survive the harsh CO2 capture process. Here I include a figure which was published just last month. Rice University group has synthesized a combined graphene oxide and carbon nanotube. This material, if we functionalize with oxygen functional group followed by the amine group, I believe this is going to be a very strong CO2 capture agent. And if we want to use this type of building blocks for capturing CO2, we have to functionalize with amine, because if we are talking about separating CO2 from hydrogen, the selectivity of capturing CO2, amine is a very critical solvent, solid solvent. Yeah, this is it. So we have quite a few concepts combined for a relatively simple experiment. Carbon fixation, CO2 fixation on the edge carbon is known for a long time. I will discuss that. And some of the work done by organic chemists on reductive photocatalytic carboxylation of fused aromatic carbon has been demonstrated about 10 years ago. And ultrasound reactions, including water splitting and exfoliation of graphite oxide. And water can serve as a hydrogen donor or OH donor, depending on the situation. So it was a trial. And hydrocarbon swelling, carbon can be swelled by CO2, which is also demonstrated. And CO2 and the high pressure after rapid expansion, it can enhance the expansion process. Biochar has a very unique structure, so we choose biochar for the current study. And the CO2 capture researchers have been working on a functionalization of solvent which can be borrowed in the current study. So, and this Kolbe-Schmidt reaction basically is a carboxylation reaction. CO2 is attached to the benzene ring next to the phenolic group. This reaction has been used in the synthesis of aspirin. And what we are interested in is if, this is quite a few years ago when we started this project, we are interested in knowing if this chemistry has been used in capturing CO2. And the first thing we looked at it was the desorption of this carboxylic group has to be in a reasonable range. And we notice it's indeed well within the amine capture process at this moment. So this is one of the our incentive. The other big incentive is the fused aromatic ring can capture CO2 in the photochemical reaction, and this product not only include CO2 group, it also involves addition of hydrogen, addition of two hydrogen, on actually two, yeah, these two, COOH and this hydrogen group on the fused ring. So the product will have higher energy content than the reactant. So what it implies is we are actually fixing CO2 on the aromatic compound, and the product will have higher energy content. We are storing photochemical resources, photo irradiation in the product. But in the reaction, the original researcher used a hydrogen donor and an electron donor. This amine is used to serve as an electron donor, so its electron can be excited by the photochemical irradiation, and propanol was used as a hydrogen donor. So what we are thinking is if biochar has a lot of fused ring, and it has titanium dioxide, it has a silicate. These compounds can serve as electron donor by themselves. And if we add water, see what happens. So this was one of the incentives. And solvent-induced swelling has been known for coal researchers for a long time. And more than that, Terry Ward and his group classified different type of particles and their behavior in gasification. If particles are hollow inside, the gasification efficiency is very high. If it's not hollow, it's solid inside, the gasification efficiency is low. So we postulate if we use CO2 and water, it can swell the char matrix. And if we use rapid expansion, it has been used by Professor Dale. If we use rapid expansion, we can further disrupt the physical structure of char. And ultrasound. This was the first group reported in 2006 that ultrasound can break up the stacks of graphite and graphene oxide, graphite oxide, I should say, graphite oxide. But later on, it was discovered the graphite can also be broken off with a certain limit by ultrasound. So that's one of the incentives for us to use ultrasound. And this is a cartoon of biochar structure. You can tell there are many graphene oxide and graphite oxide, graphene clusters. So this gives us incentive to do some treatment study. We use SOGAN. We polarize it to 550 degrees C in our combustion lab. Then we put the 3 to 6 grams of biochar in a flask, double neck flask, saturate CO2. Then we do treatment. This is a xenon lamp for photochemical irradiation. And the flask is placed in a water bath on the top of a sonicator. The sonicator has 2 dials, one for controlling the stir speed, one for controlling the ultrasound output. And we use 5-hour treatment and 3 minutes to 5 hours treatment. We start with 5-hour treatment. And after the treatment, this is what we found. This slide shows the data from magnetic stirring without ultrasound. This slide shows 3 groups of data. This column, the first column of data, represents the analysis, elemental analysis of raw char. The second column represents the analysis from thermally treated char. Thermally treated char means without ultrasound, without photochemical interaction, just put in the solution for 5 hours. at 65 degrees C. The third column of data, this group of data represent photochemically treated data. From the analysis, we noticed, the first thing we noticed is there are significant weight loss, obvious weight loss after the treatment. We burn it with a Bunsen burner, we notice there are significant ash loss. So it's reasonable. Some of the potassium, sodium can be dissolved in water. So we did analysis to those compounds. We noticed there's significant loss of potassium and sodium, and also silicon. Those three compounds are detrimental to gasification. They cause falling and slugging, and silicon cause actually retard the gasification reaction. And if we also notice for photochemical reaction, the hydrogen content increase. So our prediction seems to be correct. There is a hydrogenation reaction. Then we use ultrasound in the treatment. Well, this is Biochar again. This is thermally treated with ultrasound, but without photochemical irradiation. This shows the photochemical interaction. The result shows significant weight loss, as the previous slide. It shows loss in loss in minerals, significant loss of minerals, gain in hydrogen, gain in carbon. Notice the carbon increase is about, I believe, 30%. So we are pretty excited, and CO2 does show interactions. I'm running out of time, so I will skip this slide. And the Fourier infrared spectrum does show CO carboxylation reaction taking place, this pig. And this summarizes all the reaction without extrafoliation of the graphene layers, hydrolysis of esters, esters breakage, ether breakage. These two reactions have been mentioned earlier. Dissolution of the salt. So we believe the observation we made can have significant impact. This is what we are focusing on, to add a gasification pretreatment unit before the carbon is gasified. And also we are working on producing solvent based on graphene oxide, and probably we are going to use biochar also. This is a slide I already mentioned once. So the pretreatment unit I'm thinking about is a high pressure unit. The experiment we did was 1 atmosphere. We believe if we conduct the experiment at the 20 atmosphere, this is typically used in gasification process, the observed phenomena should be even higher. This is experiment. This emphasize the short reaction time result, and we indeed show the benefit of pretreatment. It's much higher than the overall energy output from ultrasound. For the CO2 capture process, our plan is to oxidize the graphite to form graphite oxide. Graphite oxide can be broken off by using ultrasound. Then we functionalize with amine. Then we use it for CO2 capturing process. And in the next few set of slides, it shows the amine functionalization method in our plan. There are authors recently published work showing the efficiency is remarkably well. These methods, not by ours, but very close to what we are thinking. But we are thinking to use some chemical reagent which can facilitate the reaction of graphene oxide, then capture the amine, fixed with amine, then use the other amino group to capture CO2. There are many methods. This is a graphene oxide framework, and there are photochemical reaction we can consider. We can dope the carbon material with the titanium dioxide, graphene oxide by titanium dioxide to enhance the photochemical interaction of carbon with CO2 and the water. All these are under consideration. Ultimately, we would like to know if it's possible to use biomass pulverized to produce biochar using ultrasound to break off the layers for capturing CO2. So this is our plan. If all these concepts are implemented in a traditional gasification process, we're going to add a pretreatment process. We're going to add pyrolysis of biomass near the gasification plant and produce a biochar, functionalize it, capturing CO2 in the plant. So we have our plan, and we are seeking collaborations. Biochar by itself have many advantages already. There is an international biochar initiative. So in conclusion, I'll say 2 points. The interaction of biochar with CO2 and the water can be very interesting. It's a very rich research area, particularly if we incorporate photochemical reaction and the sonication reaction. And we have a lot of work to do. Then I would like to thank SCEC organizers to invite me to give this talk, and our student and also our Office of Research staff have been very supportive to my work.